Welcome again. Today we start our next topic on algorithms design and analysis course, Knapsack Problem. Knapsack is an optimization problem in which n items are given and each item with a certain weight and profit or value. And we have to put these items or some of them in a knapsack of capacity W to get the maximum profit or value. There are two versions of the problem. 0-1 knapsack problem, in which items are indivisible. You either take an item or not. We cannot take part of the item. And the second version is a fractional knapsack problem, in which items are divisible. We can take any fraction of an item. Suppose, for example, that we have the following items. For items A, B, C, D, profits and weights for each item are given. For A, profit 8 and weight 4. For B, 10, 8. For C, 7, 3. For D, 9 and 6. And suppose that the capacity of the knapsack is 8. If we apply a greedy approach to solve this problem, we can select the item with the maximum profit or minimum weight and start with it. For example, if we select the item of maximum profit, which is B, now the weight of B is 8, so the knapsack here is full. Our profit is, in this case, 10. We cannot insert any more items in the knapsack. If we look to these items, we can make more profit if we select, for example, item A and C. The total weight for item A and C is 7, which is less than the knapsack capacity. And in this case, the total profit is 15. So greedy approach is not good for 0-1 knapsack problem. Even if we take the ratio, profit to weight ratio, this is another example with 3 items, A, B, C, profit for A, 500 and weight 40, for B, 225 and profit and weight 25, and for C, profit 330 and weight is 30. If we take the ratio, profit by weight, and apply a greedy approach, we start with maximum profit A, the weight is 40, and the remaining in the bag are 15, the remaining weight that we can pick. We cannot take B or C, since in the 0-1 knapsack problem, we have to take the whole item or nothing. So in this case, the total profit is 500. However, if we select B and C, and the total weight is 55, which is good for the capacity of the knapsack, then the total profit will be 555, which is better. So as a conclusion, 0-1 knapsack problem cannot be solved by a greedy approach. A greedy approach does not ensure an optimal solution. In many cases, a greedy approach may give an optimal solution, but it is not guaranteed. Now we move to the fractional knapsack problem. The same statement. We have n items, each with a certain weight and profit, and a knapsack with a given capacity. But now we can take a fraction of an item. If we take the same example with 3 items, now this is the ratio, profit to weight. And the weight allowed in the knapsack is 55. If we start with the maximum ratio, which is here, we pick 40 weight from A. Now we have a remaining 55 minus 40, 15 kg, for example, and we can pick fraction of B or C. Since the ratio for C is larger, we can pick 15 kg from C with a profit 165. So the total profit will be 500 plus 165, 665. In this case, a greedy strategy is good for a fractional knapsack problem since we can find the optimal solution. Remember, a greedy approach is not good for 0-1 knapsack problem. We'll use another approach, dynamic programming, but a greedy approach is good for fractional knapsack problem. Regarding dynamic programming, it's a good strategy for optimization problems. Again, if we have the lists of items and the capacity, we can solve the 0-1 knapsack problem really in two different methods. First, using binary table, I call it, like a truth table, consisting of 2 to the power n states, finding the profit for each valid state and finding then the maximum profit. This solution is like generating the whole space tree for the items and then find the optimal solution. For example, if we have 4 items and the capacity of the knapsack is 7, item 1, 2, 3, 4 with given weights, 1 with profit 1, 3 profit 4, 4 profit 5, 5 profit 7. Since there are 4 items, we generate a vector X, and in the table we list all the states. There are 2 to the power n states, like in the space tree, from 0, 0, 0 to 1, 1, 1, 1. Since 4 items, we have here 16 states. And now we start to calculate the profit for each state. Here we have profit 0. If we select 4, it's okay. The capacity allows us to do that. Then the profit is 7. If we select 3, the profit is 5. 1, 1, we select 3 and 4. In this case, the sum of weight is 9, so this is not allowed, X. If we select item 2, then the profit is 4. If we select 2 and 4, the weight is 8, not allowed. If we select 2 and 3, the weight is 7, allowed. And we continue. After completing, from the allowed profits, we choose the maximum, which is in this case 9, and this corresponds to the vector 0, 1, 1, 0. 0, 1, 1, 0, meaning that we have to select item 2 and 3. And really, item 2 and 3, the weight is 7, and the profit is 9. Do you see the complexity of this approach is very high, since the size of the table is 2 to the power n, and we have to fill or to find the profits for each state and then find the maximum value. So if n is high, then the complexity of this approach is exponential. although it's very easy to implement. Next, we will solve this problem or this example using dynamic programming. These are the steps that we should follow. You will understand these steps better with an example, but a quick trace, we generate a table. You see, when we use dynamic programming, always we have to generate tables, so the space complexity is higher, but it guarantees the optimal solution. The table of size n+1, w+1. We fill the first row and the first column with zeros. Now we start filling the other entries of the table using the given formula. If j less than wi, then we just copy the above cell to the current cell. Otherwise, we have to choose the maximum, the above cell value, or the maximum profit made by item I plus the profit from the remaining weight. After filling all the items in the table, the maximum value will be on the last entry in the table. I'll demonstrate this through an example, the same example. Suppose again we have the previous example. The capacity of the knapsack is 7. 4 items are given with the weights and profits. Here is our table. Here is a table of size 5 rows from 0 to 4 and 8 columns. Since the capacity W is 7, then we have 8 columns for each weight. I wrote here outside the table the weight and the profit for each item, so it will be easier to follow. After filling the first row and the first column with zeros, we start the process of filling the other entries in the table using the given formula. Do you see the logic on filling the table? Now, if we have item 1 with weight 1, we cannot put item 1 in a 0 weight knapsack. If the capacity of the knapsack is 1, we can put it, and the profit is, in this case, is 1. Here we write the profit. And in all other cases, in the same manner, we have a profit of 1. Do you see all the entries in the table represents profits? Now regarding item 2, now we have item 1 and 2. Here we have 0. Can we put item 2 with weight 3 in a knapsack with weight 1? No. So we copy from the above cell in this case as well, but we can put item 2 in a knapsack with capacity 3. Its capacity is 3. Here, if this value is greater than the profit plus the profit from the remaining weight, then we copy, but we have to select maximum from this value, and if we put 2, then we have a profit 4. We cannot put anything else since the weight of item 2 is 3, so the profit is 4, the maximum between 4 and 1. Next, can we put item 2 in a knapsack of capacity 4? Yes. In this case, we have a profit 4, but we have 1 extra weight. Since we have 4 here and the weight of item 2 is 3. So we go back to weight 1 and its profit is 1 in the above cell. So 1 plus 4 is 5. The maximum between this one and 5 is 5. We continue in the same manner. I will trace from here. For example, if we have to fill this entry, how to fill this entry. Do you see from the above cell, the profit is 6. But now we have to compute the profit plus the remaining profit. Here the weight is 5. So if we pick item 4, which weight is 5, then the profit is 7, which is larger, 6 or 7? 7. So we write here 7. To fill this one, the profit in this cell is 6. But if we pick item 4 with weight 5, the profit is 7, plus the remaining profit, 6 minus 5, 1. We go here to weight 1, the profit is 1. So 7 plus 1, 8. For the last cell, here is 9, but here also, if we pick item 4 with weight 5, we have 2 remaining kg. So we go to 2, the value is 1. So 7 plus 1, 8. 9 is larger. So here now is our maximum profit. To find out which items we have to select to gain this maximum profit, we have to trace in the table. This item did not come from here. It came from here. So item 4 should not be selected. Now this 9 did not come from the 5 here. It came from 6. So we select item 3. The weight of item 3 is 4. The remaining weight is 3. So in the above row, we go to weight 3 here. This value came from here, not from here. So we select item 2, and the total weight is 7. We go, when we reach the first entry in the table, then we are done. So items 2 and 3 are selected with the maximum profit 9. Regarding complexity, each entry of the table requires constant time big O of 1 for its computation. We have the total entries NW. So big O in this case is NW to fill all the entries. It takes big O of n time for tracing the solution, since tracing process traces the n rows. So finally, big O is NW to solve 0-1 knapsack problem using dynamic programming. The space complexity is big O NW as well, since we need extra table with size n plus 1 W plus 1. This is the Python code for the 0-1 knapsack problem using dynamic programming. We have the two lists and the capacity, the knapsack capacity. We pass to the knapsack function the weight for the knapsack and the list of weights and the profits, and in here we create the table of size W plus 1 N plus 1. We fill the first row and the first column with zeros, this statement. And here we fill the entries in the table using the formula above. If the weight of I minus 1 is greater than W, then we copy the above cell, else we choose the maximum value from between the above cell and the profit of this cell plus the remaining profit. And we retain with the maximum profit the last entry in the table. At the end, please remember that a greedy approach does not guarantee an optimal solution for 0-1 knapsack problem. It finds the optimal solution for fractional knapsack problem. The optimal solution for 0-1 knapsack problem can be obtained using dynamic programming. For now, thank you.